go. This is going to be the answer to the question I posted in yesterday's stream. Today is Thursday, November 26th. You're not going to be able to read that. See from there that you can't read it. So a perfectly insulated bucket holds 26 liters of water at 15 degrees Celsius. We assume the density of water is 1 gram per centimeter cubed. And that, and I'm going to show you this on the camera so you can freeze frame it. I'm showing it on the other camera because that's the one you're going to be able to watch later. This is what I'm showing the other camera. I don't know if you could take a screenshot of that if you want. I'll give you 5 more seconds. 5, 4, 3, 2, 1. Time's up. So let's do the answer to it. So a perfectly insulated bucket holds 26 liters of water with a density of 1. The specific heat capacity of water is 4.186 joules per gram degree Celsius, which means it takes 4.186 joules of energy to warm up 1 degree of water by 1 degree Celsius. A cube of lead, 11 centimeters high, is heated to 193 degrees Celsius, is placed in the water, and the density of lead is 11.32 grams per centimeter cubed, and the specific heat capacity of lead is 0.159 joules per gram degree Celsius. Assuming all of the specific heat capacities remain constant over the temperature range of the experiment, and that all the heat is kept within the system, we'll pretend that none of the heat leaks out of the experiment, which of course is unrealistic, but this is what we do when we do chemical and physical experiments. You have to make little assumptions that make the calculations easier. So what is the final temperature of the water and the lead? So this experiment is going to be based on the premise that the hotter object warms up the colder object, and the hotter object cools down until it reaches the equilibrium temperature, while the colder object warms up until it reaches the equilibrium temperature. And that equilibrium temperature is obviously the same for both things, because the hotter object stops cooling down and the colder object stops warming up when they both achieve the same temperature. So we're going to start by finding out how much lead we have. Density is equal to mass over volume. Therefore, we can rearrange the equation to solve for the mass of lead. Density times volume is equal to mass. The density of the lead is 11.32 grams per centimeter cubed. There's 11.0 centimeters high cubed, so we're going to raise that to the power of 3. And when we multiply all that out, we're going to get centimeters cubed here. So that centimeters cubed is going to cancel. What you get is 15,066.92 grams of lead. At this point, you should be able to do these calculations because I drummed it into your heads all through grade 9, 10, and 11 if you had me. The mass of the water. How much water do we have? It says that the density of the water, again, it's going to be related to density times volume. The density of water is 1 gram per centimeter cubed. And the volume of the water, we're told, is 26 liters, 26.0 liters times 1,000 milliliters per liter times 1 centimeter cubed per milliliter. The two are basically interchangeable. Centimeters cubed and milliliters are the same volume. So that gives you 26,000 grams of water. Now, the heat lost by the hot lead is going to be equal to the amount of heat gained by the cold water. This is a reflection of this law, the conservation of energy. the energy doesn't disappear magically, it just goes somewhere else. So let's replace the Q with what the heat flux equation tells us. Q is equal to mc delta T for the warming or cooling of any object, where m is the mass of the object, c is the specific heat capacity of the substance, and delta T is the change in temperature. And so we're going to say mc delta T for the lead is going to equal to mc delta T for the water. Now let's substitute the variables. We have 15,066.92 grams of lead, the specific heat capacity of which is 0.159 joules per gram degree Celsius. I recommend strongly that you write your units in so that you can see how it all cancels and gives you the answer. Now, for the delta T, I don't know what the delta T is, so what I'm going to do is I'm going to substitute delta T with two subscripted variables. Delta T is basically temperature final minus temperature initial, or temperature initial minus temperature final. How do you decide which one to use? Use the one that gives you positive values. And the reason I do this is to avoid having to worry about the sign conventions, because you'll end up making a mistake. I'm the teacher and I make mistakes when I try to keep the sign convention straight. So to avoid all the sign convention nonsense, I know the hotter stuff is giving energy to the colder stuff. So to avoid all the sign conventions and the complexity that it brings, I'm just going to work with the absolute value. The temperature change is all I'm interested in. But we do know that both of these will have the same TF. So just arrange it so that you get a positive number for the temperature change. So because the lead initial temperature is 193 and then it cools down to some final temperature, I'm going to write it this way for the lead. And for the water, we have 26,000 grams of water. We have a specific heat capacity for water of 1.86 joules per gram degree. Now before you all go crazy and say, but sir, it says 4.184 in your other notes. Yes, I know. That's for when the temperature goes from 14.5 to 15.5. The specific heat capacity of water as defined in the SI system has been moved up to 4.186 because it changes a little bit as the water goes through, starts to warm up. So that's the one I used in this particular problem. If you use 4.184, it's not going to give you a wrong answer anyway, because there's only 3 sig figs in this question anyway, so you're going to have to report it to 3 sig figs. It's going to be eliminated anyway. So TF minus 15 degrees is, so the final temperature of the water is higher than its initial temperature, so to get a positive number, that's the way I arranged it here. Now we solve for TF. So I'll give you one intermediary step, or two. So you get 462, and you'll notice, by the way, grams cancel, and this one is in degrees Celsius, so the degrees Celsius cancel here. And this is also in degrees Celsius outside of that bracket. So the grams cancel here, and the Celsius cancel there. So your answer is going to be in joules versus joules. And then your when you solve for TF, yeah, you're solving for TF, which is going to be in degrees Celsius. So you're going to get 462,358.574. And I'm not going to write units at this point because it's going to clutter it up. Minus 2395.64. I hope you can see this. 028 TF, and that's going to equal 108,836 TF minus 163,002. 1,630,540. That's what I'm getting. 2,098,898.574 over 111,231.6403. When you find that out, you get 18.833,657. You're only allowed 3 sig figs, so your answer is 18.8 degrees Celsius. So the lead is going to cool down until it hits 18.8, and the water is going to warm up until it hits 18.8. So the final temperature of your system when you mix those two things is 18.8 degrees. We will get more such sample problems as we progress in our abilities. The next thing I want to do is work some sample problems from the book with you. So just hang tight while I get chapter 5. When you come into class next week, I'm also going to give you a couple handouts. Just remind me if I forget. I got these ones for you and these ones. So they're going to be waiting here for you. Chapter 5. No. That's that. Now, obviously, you don't have access to. I'm going to have the photocopies of the text for you. So I'll work out the problems with you, and I'll also write the question out for now, until you can get your hands on the text itself. The first one I'd like to try with you is, what is the kinetic energy in joules of an argon atom a mole? What is the kinetic energy in joules of A, an argon atom moving with a speed of 650 meters per second? B, a mole of argon atoms moving with a speed of 650 meters per second. Hint, 1 AMU is equal to 1.66 times 10 to the minus 27 kilograms. So let's do that calculation. This is from page 172, so it's a practice exercise from page 172 of the text, and which is brown. So they're asking A, kinetic energy of one argon atom moving at 650 meters per second. Well, argon has a molar mass of 39.948. So argon equals 39.948 grams per mole. So let's find out what one atom weighs. Therefore, one atom is 1 over an Avogadro's number, 6.02 times 10 to the 23, times that mass, 39.948 grams per mole. And so let's find out what the mass of one argon atom is in grams. Then we'll convert it into kilograms, because the kinetic energy formula requires the use of the units of kilograms. So I'm going to use the embedded Avogadro's number, so it's constant number 28, 6.022140857 times 10 to the power of 23. And I'll take the reciprocal of that number by putting 1 over x function. So second function, x to the minus 1 equals an invisible number. Why is it doing that? Why? Because I got it set up wrong. I want scientific notation, which is number 1, and I want 9 decimals. All right, what we get is, the reciprocal of that number is 1.66053,904 times 10 to the negative 24. So that's what one atom is going to be in comparison to the number of atoms there are in a mole. And then we're going to multiply it by the mass of 1 mole of atoms, and then we'll get a fraction of what the fraction of that weight of 1 atom would represent. So 39.948 grams per mole. Times, what would be the units on this? This would be atoms per mole, moles per atom. Right, so the moles cancel, and that's going to give you grams per atom. So times 39.948, and you get 6.63352136 times 10 to the negative 23 grams per atom. Let's go to kilograms, because the kinetic energy formula requires that, times 1 kilogram per 1,000 grams, and you'll get the same number, 6.63, etc., times 10 to the minus 26 now. You add 3 zeros to that, that's what you're going to get. Kilograms. Now we can enter it into the kinetic energy formula. So kinetic energy of anything is equal to 1/2 its mass times its velocity squared. In this case, the mass is 6.63, etc., times 10 to the negative 26 kilograms, and its velocity is 650 meters per second. And then we get to square that velocity. So let's see what that gives us. Times 650 squared equals, divided 2, that's equivalent to saying times 1/2, and you get 1.40133139 times 10 to the negative 17 joules. That's the kinetic energy of 1 atom. I hope you can read this. Yeah, I can read it, so you probably can too. The next part of the question asks, a mole of argon atoms moving with a speed of 650 meters per second. So now, okay, the book says 1.4 times 10 to the minus 20 joules. Why am I getting to the negative 17? I know when. Because that was in grams, so I go to kilograms. Let me just double check here. 6.63352.136 exponent negative 23 divided 1,000. Yeah. Times 650 squared times divided by 2. Okay, why did I do that? I don't know. I forgot to enter something. Oh, I didn't do the actual multiplication in my calculator, so it's minus 20 joules. Yes. All right, so that's the correct answer for 1 atom. Now let's find out for a whole mole of atoms. Well, to do that, just multiply by Avogadro's number. So times 6.02, etc., times 10 to the 23 gives you for the kinetic energy for a whole mole of atoms. So times exponent 28, which is embedded in my calculator, and you get 8.439 times 10 to the 3 joules. Or you could say 8.448 argon gas at, with a speed of 650 meters per second on the average, would have 8.4 kilojoules of energy in it, just from its molecular motion. Which is how you can see that, obviously the gas, if it's moving around, it's not anywhere close to absolute zero. But if you were to cool that gas, you would take away its kinetic energy, and eventually the gas would stop moving, it would freeze. You could freeze argon into a solid, and if you kept on lowering the temperature until the temperature reached negative 273 Celsius, which is the coldest temperature you can reach in the universe, 273.15 below zero to be precise, and you get what's called absolute zero, 273.16, sorry. So that's absolute zero. That's the coldest temperature you can reach. At that temperature, it is now impossible to extract any more heat because there's no more molecular motion. So there's no more heat. Once there's no more heat, it's the equivalent of total darkness. Can anyone see the answer? You can't see the answer? 8.44? It's right here. That's too small to see, Ramella? Is it too small to read? Are you using your computer? It's a bit blurry. Okay, I'm gonna write it bigger. I'm gonna write bigger. Maybe I should move it to just one. Would you prefer it if I put it to one board? I could close it up so that you only see one board at a time, but then I have to keep on moving it back and forth. I don't mind, but if you want, I'll do it. No answer? Okay, I'll just write it a bit bigger. Let's do the next one, the next practice exercise. The next practice exercise addresses the question of energy and sign conventions. Okay, it says, calculate the change in the internal energy of the system for a process in which the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. So let's write the conventions down before we solve the problem. So sign conventions for Q, W, and delta E. So for Q is positive. Positive means gain of heat by the system. Negative sign means it loses heat. So let's give you an example. If I warm up a cup of coffee in the microwave, I'm putting heat energy into it by exposing the water molecules in the coffee to microwave radiation. So in your microwave, basically, you have a generator of electromagnetic radiation, radiation that you can't see with your eyes. And the effect this radiation has on water molecules is to make the hydrogen atoms spin faster. So the hydrogen atoms spin faster, and it ends up causing the whole molecule to vibrate, for the bonds to stretch, and the molecule can start spinning itself. So it increases all the other forms of motion in the molecule, but the thing that microwaves specifically do is they make the hydrogen atom spin faster in place in its bond. You know, microwaves were actually an accidental discovery. They were doing research during the Second World War into radar technology, and the technicians noticed that every time the antenna that was spinning around to send out a radar wave so they could locate enemy planes or even their own planes, every time the antenna faced them for a second, they would feel a rush of warmth. They actually felt warmer, so they realized the antenna was emitting radiation that interacted with the water in their bodies. So they did experiments with it, and they tuned it to a frequency, I can't remember if it was higher or lower, and they realized that that's where microwaves are, and microwaves are very effective at warming up water molecules. So that's what your microwave system is. It's just a generator that emits electromagnetic radiation in the microwave range that warms up water molecules. There is some controversy around microwaves and certain forms of radiation because some of the resonant frequencies of those waves are believed to cause vibrations within the body. For example, if it vibrates your DNA backbone at the right resonant frequency, it can cause breakages in your DNA backbone, which over time can lead to mutations and other problems within the body. So there's some controversy around exposure to high intensity microwave radiation. So if you're holding your cell phone next to your ear, it's probably not a big deal. But say if you stay with your cell phone all day next to your ear, you might end up having a higher risk of cancer. That's what some of the studies seem to suggest. And definitely, if your apartment is located under one of those big microwave antennas, I wouldn't be moving into one of those, just because there you're having the transmitter intensity is extremely high because it has to cover a wide range. There you're exposed. If there is some truth to the rumors that it has an effect on the DNA, you might be exposing. Well, you'd be the first to find out because that's where the intensities of that radiation are very high. So let's continue with our sign conventions. So Q means gain of heat. So if you put your coffee in the microwave will warm up the cup of coffee. That means you put energy into it. You'd have a positive sign for Q, which is the heat flux. And when you take your coffee out and put it on the countertop, it starts to cool down. That means it's going to be giving heat energy to the environment. It's losing heat energy, so it's going to have a negative sign convention. That's what this means. For work, positive means work done on the system. And negative means work done by the system. By the way, a little warning, do not discuss this with engineers in university because their sign conventions are reversed. So you'll only get confused. If you talk to engineers talk about when the system does work, they call it positive, and when the work is done by the system, they call it, work done by the system they call positive, and work done on the system they call negative, because engineers, their mentality is machines doing work. So their sign conventions are reversed to chemists, and if you talk about thermodynamics with an engineer, you're going to hit that snag and you're going to get confused. So don't talk to engineers in university. Just talk to other chemists. For delta E, plus means net gain. Of energy by the system. And negative means net loss. By the system. This is in your textbook. This is from Brown et al., meaning and others. A bunch of other guys named there were authors of the textbook. On page 174. This is the 10th edition, by the way. So here's your practice exercise on page 174. Calculate the change in the internal energy of the system for a process in which the system absorbs 140 kilojoules of heat from the surroundings and does 85 joules of work on the surroundings. So we're going to say delta E is equal to Q plus W. So it's the system absorbs 140. So the system has gained heat. So it's plus 140, and does 85 joules of work. So if it's work done by the system, it means it's a negative sign. So the work is negative 85. So the delta heat for this is going to be 55. Change in internal energy for the system is plus 55 joules. Can you read it now? Is that big enough? No answer. What, are you all having a sandwich or something? Did y'all go to the kitchen? Leave me alone? Tell me, can you read that last bit here? Can you read this? Who's at the top of the list there? It's better. Daniel, can you see it? I didn't hear anything. Is my speaker off? I can't hear you. Hold on a second. Just noticed it now. Usually you guys don't talk much, so I didn't think it was anything wrong. Where's the host controls? No. Turn off microphone. There's no. Use a phone for audio. You know what? I thought I answered all the questions correctly at the beginning. Apparently I didn't. Settings. Okay, here, let's see this. Default speakers. Speaker. Hey, somebody say something. Say hello, Daniel. Unmute your mic. I saw it unmute, but I didn't hear you say anything. Test. Hello? Okay. Okay, now I hear you. The speaker volume was all the way down. Sorry about that. Okay, now I hear you all. Good. Hey. You know, there's one thing to be said about this distance learning. I don't have to worry about kids talking in my class. I'm here all alone. It feels like I'm in a little cage all by myself. I have no idea what you're doing at home. And of course, none of you put your faces on there. No pressure, but it wouldn't be nice. It wouldn't be a bad thing for me to see you, just so I could see your facial expressions, whether you're falling asleep or not. Not that it's going to make a difference. You still have to get through this material. All right, 72. Hey, where's 72? There it is. Okay, 73. 74. System doing work on the surroundings, that's what we covered. You should, by the way, tonight, you're going to do yesterday I told you to do notes, make notes on parts 4. Tonight, and part 5, and I added 2 more. I put yesterday's lecture as 4B and 4C, so you should watch those again if you want to get an explanation of the definition of enthalpy. And tonight you should definitely watch part 6 and 7, and make notes. Okay? So let's continue now with some of the examples that are in the book. The next thing we're going to look at is enthalpies of reaction. So, Daniel, your mic is on.
My bad.
It's okay. The next thing we're going to look at is enthalpies of reaction. So enthalpies of reaction is on page 180 of the textbook, and you'll see when you get it on Monday. You can find out the enthalpy of a reaction, how much heat energy a reaction puts out, by looking up the enthalpies of formation of the products and the enthalpies of formation of the reactants. You can think of a chemical reaction as a transaction, where each chemical has an innate amount of energy. and it just sort of sits on a certain level on a hill. Think of yourself as sitting on a hill at a certain altitude, and then you go through an interaction with another chemical, and all of a sudden it changes you into a different chemical, and now you have a different amount of energy, and you're in a different place on the hill. So that's what happens when chemicals interact. They change their shape, they become different molecules, and then they become molecules that have higher or lower energy. For example, when dynamite explodes, it turns into nitrogen gas and oxygen gas and all the other gases that are produced in an explosion, all of which are much lower energy content than the dynamite molecule. So that difference in energies is what's released in the explosion. That's a more dramatic example, but every chemical reaction, like the burning of fuel, if you burn octane from your gas tank in your engine, what comes out of the exhaust is carbon dioxide and water. Carbon dioxide and water are low energy molecules by comparison to octane. In your body, you burn lipids. Say if you fast, if you don't eat any food, then your body's going to start breaking down the fat under your skin, and that's also in your muscles and everywhere else in your body, and it's going to start turning it into CO2 and water. When you breathe out, what you're breathing out is the waste products of that metabolic process. And I've told all my students this before, when you lose weight, it's through breathing. Every time you breathe out, you get a little bit lighter. Why is that? Because there's CO2 and H2O, and some of that H2O is not just the water that evaporates from your mucous membranes, it also happens to be metabolic water that is produced from the combustion of the fatty acids in your body. So all the carbon that you breathe out in the form of CO2, where's that carbon coming from? It's coming from the carbs and the fats that you're burning in metabolism. If you could stand on a super sensitive balance that could measure down to the milligram level, you would see your weight drops every breath. Every breath you take, you're getting a little bit lighter. And that's why if you don't replenish that weight by eating more food, you essentially waste away in a matter of a few weeks or months, depending on what your body weight is. If you weigh 500 pounds, you might last a few months. If you weighed 100 pounds, you wouldn't last that long. So when you do enthalpies of reaction, you can discern what the energy change of a reaction is based on the participants in the reaction. So let's do one of those together. This is on page 182, practice exercise. It says, hydrogen peroxide can decompose to water and oxygen by the following reaction. And it says, calculate the value of Q when 5 grams of peroxide decompose at constant pressure. Let's look at the reaction first of all. So this is not, this is just looking at the whole reaction. Later on, we're going to look at the smaller parts of the reaction. This is practice exercise on page 182 of your text. So hydrogen peroxide, it's H2O2, and it's a liquid, and it decomposes into water and oxygen gas. And when it does that, for every mole of oxygen produced, and for every 2 moles of water produced, you get an output of negative 196 kilojoules. So it releases heat energy. So if you had 5 grams of peroxide decomposing. Oh, I haven't done it. I'm going to bring them later.
You gonna bring it later?
Yeah, I'll bring it later. Sorry.
No problem.
So if you had 5 grams of peroxide, first of all, let's find out how many moles of peroxide that corresponds to. Peroxide has a molar mass of 2 times hydrogen, which is 1.00794, plus 2 times oxygen, which is 15.394 grams per mole. So, how many moles of peroxide is that? Let's find out. I have not done this, well, I may have done this calculation somewhere else, but I did not, couldn't find it, so I'll do it over. So 2 times 1.00794 plus 2 times 15.394 gives you a molar mass of 34. So you have 5 grams of peroxide and it has a molar mass of 34.01468 grams per mole. So that means that you have 0.146995356 moles of peroxide. But remember, for the burning, for every 2 moles of peroxide burned, you get that much energy released. So times negative 196 kilojoules per 2 moles let's incorporate that later. Let's pretend it's for 1 mole, okay? So yeah, that many moles of H2O2. Let's pretend it's for 1 mole, and then we'll do the other part after. So times 196 gives you 28.8, negative 28.8, 11 kilojoules. But remember, it takes times divide by 2 because it takes 2 moles per that amount. Actually, I should have just written it here, per 2 moles of peroxide, yeah. That's a better way to incorporate it. So divide that number by 2, and what you get is negative 14.4 kilojoules. After sig figs, you only have 3 sig figs. Yeah, so you got to keep in mind when you do the calculation to remember that this coefficient has an effect on the answer you're going to get. If this coefficient had been 1, then you would have gotten 28.8, but because it takes 2 moles to get that amount, then it reduces the amount of energy you get. All right, the next one is calorimetry. I'm just going to do one more, the one on page 184, because that's a lot of material. Again, I hope you're writing the notes for tonight. It'll be parts 6 and 7 on the video, and then I'll continue tomorrow doing more practice examples from the chapter. The next practice example is on page 184. It says, large beds of rocks are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram degree Kelvin. For some reason they use Kelvin on this one. But the Kelvin degree and the Celsius degree are the same size. They're just, the scales are 273 degrees apart. So 0 degrees Celsius is equal to 273 Kelvin. Why do they have this different system? Because the Kelvin scale is the absolute temperature. Absolute temperature means that when you go to 0 on the Kelvin scale, there's no more heat. If you go to 0 on the Celsius scale, there's still tons of heat. They just use the Celsius scale because it's more convenient, because it corresponds to the melting point of water, which is 0. But when you're doing scientific calculations, 0 means no more heat, whereas 0 on the Celsius scale means just the melting point of water. So, large beds of rocks are used in some solar heated homes to store heat. assume that the specific heat of the rocks is 0.82 joules per gram Kelvin. Calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees Celsius. B, what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? So for this, we're going to modify our Q is equal to MC delta T, because in this case, do we have to, actually, no, we don't have to modify it, because we have a massive rock, we have a specific heat capacity for the rock, and we have a temperature change. So no, you're still using Q is equal to MC delta T. There are examples where they just give you a heat capacity, not a specific heat capacity. So the difference between a heat capacity and a specific heat capacity means a specific heat capacity is per gram of substance, or sometimes per mole. Whereas a heat capacity is you're looking at a whole thing. You could say, for example, what is the heat capacity of this large block of metal? And you're just looking at the whole piece of metal, you're not concerned about its weight. How much energy do I have to put into that block of metal to make its temperature rise by 1 degree Celsius? That would just be heat capacity. But when I say specific heat capacity, that means I've also included a per gram condition. So this is not a case of heat capacity, this is still specific heat capacity because they give you all the parameters that you need. So the mass of the rocks in part A is 50 kilograms. And they gave you the specific heat capacity in joules per gram, so be careful there. It's 50 kilograms of rocks, so you got to convert the mass of the rocks into grams. It's 1,000 grams per kilogram. You know what? That's upsetting when you get that in a test and you forget to convert it and you get an answer that's off by a factor of 1,000. The specific heat capacity of the rocks is 0.82 joules per gram degree Kelvin. And the temperature change is 12 degrees, so 12.0 degrees Celsius. Let's see how much energy that is. So 50 times 1,000 times 0.82 times 12 gives you 4.92 times 10 to the power of 5 joules of energy went into warming up those rocks. Now, when the sun goes down and the ambient temperature decreases to below the temperature of the rocks, those rocks are going to start re-radiating that energy back out. And that's why your choice of construction materials can have a big effect on how comfortable your house feels. I don't know if you've ever noticed in the summertime, when you go downstairs in the basement of almost any house, you'll notice it's noticeably cooler. Why does that happen? Well, two reasons. One is because heat tends to rise. And the second reason is you're surrounded by concrete. You're underground and you're surrounded by concrete. Concrete tends to transpire humidity, which can also give you a feeling of dampness and can make you feel colder than you actually are. But it also absorbs heat energy and re-releases it at a different time. So when it's really hot outside, it's a lot harder to warm the basement. And then by nighttime, when it has warmed up a bit and it's colder outside, you might even find it warmer in the basement. Although typically whenever you go into a basement, it always feels a little bit cooler than the downstairs, and that's because of the fact that heat rises. We're not finished our question. It says that what temperature change would these rocks undergo if they emitted 450 kilojoules of energy? All right, so let's do it again. Except now the variable is going to be that we know the Q, we know the M and the C, which is are looking for the delta T. And so Q is equal to MC delta T. We're going to do it again. I'll do it over here because it's going to be too crowded. So this is practice example on page 184 again, but part B. We're going to say Q is equal to MC delta T. Q equals 450 kilojoules, which we're gonna turn into joules, so it's 1,000 joules per 1 kilojoule. So it's 450,000 joules is emitted. Okay, and we're trying to find the delta T, so let's isolate for delta T. Q over the MC is gonna give you the delta T. And the Q again is 450,000 joules. The mass of the rocks was 50,000 grams, as we calculated earlier. And the specific heat capacity is still 0.82 joules per gram degree Kelvin. And grams will cancel, joules will cancel, so you're left with a temperature change. Let's see what that gives us. 450,000 divided 50,000 divided 0.82 equals, you get 10.9756 degrees Kelvin change. I think we're only allowed 3 sig figs in this equation, so we're going to say 11 degrees is your answer. I don't know if you put the degree symbol for Kelvin. I don't see them doing that.
What do we get? Yeah, 11 degree decrease.
And of course, as the bricks give off the heat, it helps the house, or the occupants of the house feel warmer. Or at least you feel warmer if you're standing outside the wall. Usually houses have insulation. Depends on the houses. If you go to some places outside of Canada, some countries don't even have insulation on the houses because the climate is more temperate. I know in Italy, some houses don't have anywhere near the insulation that you see here, so it can actually feel pretty chilly in the winter. And the winter temperatures might go as low as 5 above 0, not like here where we get, sometimes we get minus 20. Okay, I'm gonna stop there because I don't know where you are and how much of this you're understanding. My guess from past experiences is that you're feeling overwhelmed. So watch those videos, make notes on 6 and 7 tonight, check out those practice examples, and then you'll get the text soon enough. I'm going to post 186 tonight. I'll give you the question, and it's an example of an experiment done with a coffee cup calorimeter, where they use data where the reaction produces an increase in temperature from mixing two things. So I'll take a picture of the question, post it, and then I'll also work it out for you and post that. Okay? And then we'll see you tomorrow. Okay? So your work starts now watching videos. The class is not over. Now it's the part where you take over and self-motivate without my supervision. That's how you can tell a person is reaching the cusp of adulthood. They don't need supervision. They self-motivate. They do it on their own. So make me proud. And I'll see you tomorrow.